This is a walkthrough of Problem 3 on Exam 1 in Module 3 of the book Problem Solving Guide for Mechanics and Thermodynamics. Problem 3 is a 5 kilogram block is being held on a 40-degree inclined plane by a horizontal force. The coefficient of static friction between the block and the plane is 0.4. What are the minimum and maximum values of the horizontal force that will keep the block at rest? Got to take inventory here. What's going on? If there were no friction, then there's only one horizontal force that will keep it there. If you push harder than the minimum, it will go up. If you push less, it will slide down. But with friction, there's a range of forces. You can imagine exerting a force that just barely keeps it there and then start pushing. It's not going to move until you break the static friction. It will go up the plane. So the question asks for the minimum and maximum value of the forces that will keep the block at rest. When pushing with the minimum force, the frictional force is helping you. It's helping you keep the block on the plane, so it's upward along the surface. When pushing with the maximum force, it's just about to go up. The frictional force is downward along the surface. So now let's focus on the minimum. There's the minimum force. There's the gravitational force. Friction is up the plane, and the normal force is perpendicular to the plane. These forces must sum to 0. Now we have to choose a coordinate system, and let's just make the x-axis horizontal. In the x direction, let's think about this before we look at the equation. In the horizontal direction, we have a frictional force, a component of the frictional force, pushing it to the right. F min is all to the right, and F normal has a component to the left, and those must balance. Sum of the forces in the x direction is ma sub x, which is 0. So Fr cosine 40 is in the positive direction, all of F min is in the positive direction, and Fn sine 40 is backwards, and those must balance. There's 3 unknowns here. We can eliminate one by recognizing that we're just about to break the static frictional force. So we're using the maximum we possibly can. It's about to come down. If I reduce the horizontal force by a small amount, the block will slide down the plane. So the frictional force is the coefficient of static friction times the normal force. It's given that mu static is 0.4, so we can substitute it in. 0.4 times Fn is the frictional force. Now we have one equation and only 2 unknowns. We need another equation, and we can get that from the vertical direction. Sum of the forces in the y direction is ma sub y, which is 0. So we have the normal force upwards, a component of the normal force is upwards, a component of the frictional force is upwards, and these 2 components are holding up the mass, holding up the block. They're going to balance F gravity. So Fn cosine 40 is directly upward. The frictional force sine 40 is directly upward, and gravity is all in the downward direction. So that's the equation. We can substitute mu static Fn for the frictional force. There it is. Here's the frictional force, mu static Fn. We can solve this for Fn, and we can divide by the factor in front of the Fn, and we can solve it. It's 1.023 mg. Little bit bigger than the weight. Our expression for the forces in the horizontal direction is frictional force cosine 40 plus F min balances Fn sine 40. We can factor out, we can solve this for F min, and we can factor out the Fn. So now we have an expression for Fn right here with only mg in it, and we can stick it in right here, and we'll be able to calculate F min. So for summary, in the x direction we have this. We need Fn, and we got Fn from the y direction. There's Fn. We plug that into the equation for F min, and we get this. And now we just plunge the buttons on the calculator, and we get 0.329 mg, which is less than 1/3 of the weight of the block, 16.4 newtons. So that's the minimum. Now we do the maximum. The gravitational force is the same, of course, but now the normal force will be larger because F max is jamming that block into the plane. There's F gravity, there's F normal. The frictional force is down the plane because it's just about to go up the plane. The frictional force is hanging on. So now the direction of the frictional force has changed, and some magnitudes have changed. In the horizontal direction, all of F max is positive. There's components of Fn and Fr backwards in the x direction. So it looks like this: F max minus Fr cosine 40. That's this one right here. Minus Fn sine 40. That's this one right here. Those all must balance. We can substitute in mu static Fn for this frictional force. And we can solve this for F max by putting these two on the other side of the equation. There it is, after factoring out the Fn. In the vertical direction, Fn is holding up everything. Fn is the only positive force in the y direction. So we have a component of Fn cosine 40, and we have some of Fr going down, and we have all of F gravity going down. So there's the positive force in the y direction, Fn cosine 40. A component of the frictional force is downward, mg is downward, setting that equal to 0. Substitute mu static Fn for the frictional force. Solving this for Fn, we get that, and we can calculate what it is. It's almost twice the weight of the block. It's big. We're jamming that block into the plane. Substitute this expression for Fn into the expression for F max, similar to what we did before, and we just calculate it. And we get 1.87 mg, which is big. Almost twice the mass. So F max is 93.3, F min is 16.4 newtons. So if we add these four vectors head to tail, which way will the resulting vector point? Let's do it. When we just sketch the force diagram, we don't know the relative lengths of the vector, but now we do, because we solved the problem. The gravitational force is 50 newtons. The horizontal force needed to prevent the block from sliding down the plane is 16.4 newtons. The normal force was 1.023 mg, which is 51 newtons. The frictional force is mu static Fn, which is 20.5 newtons. So now let's put these on the diagram to scale. So there's 50. The minimum horizontal force is 16.4 newtons, less than 1/3 of that. The normal force has to be perpendicular to the plane. We're doing head to tail here. And it's a little bit longer, slightly longer than F gravity. There it is. There's the normal force. And then we have to put the frictional force in, which is 20.5 newtons. We just calculated it. And there it is. So the sum of the forces is indeed 0. The vectors end up where they started. Now let's do maximum. It's going to be hard to get these on the diagram. They're a lot bigger. The gravitational force is the same, 50 newtons downward. But now we have this F max horizontally, which is 93.3. Much bigger than gravity. The normal force is almost twice. It's even bigger than that, 98.2, almost twice the mass. There it is. Frictional force, mu static N, F sub N, 39.3 newtons, and it's down the plane. Back to the beginning. Again, the result is consistent with the sum of the forces equal to 0. Second bonus, why is the frictional force bigger here? The coefficient of friction is the same, it's 0.4. The reason is the normal force is bigger, as I know you knew. That's problem 3.